Okay, so let's look directly at changing the radius. This is going to be four masses that are initially distributed further away from the center, the axis of rotation, and then they contract. So when they contract, we want to know how fast they're going at the end. And we're going to use the concept of angular momentum conservation, and we use the capital L, in case you haven't seen that before, to denote angular momentum. So angular momentum is conserved, so this is going back to this I initial, I1 omega 1 is going to equal I2 omega 2. Or the initial angular momentum will equal the final angular momentum. This is what I hinted at in the beginning, and so now we can actually see this in motion. Now, the trick here is deciding how to determine my inertia. And remember, if I have multiple masses, just like the previous problem that we did, if I have multiple masses involved, then all I have to do is figure out the inertia of each. These are each identical balls, so they're going to be treated as point masses. I equals mr squared, where r here is going to be the distance from the mass, the center of mass, to the axis of rotation. So our r initial is 1 meter, and our r final is going to be a half a meter. All of the masses are identical. Let's go ahead and write this out. And I wonder if you're looking at this and you're feeling a little bit panicked because you're like, but you didn't tell us what the mass is. Do you think it matters? Because remember, there's one thing I always tell you all to do is to write these things out. Don't just assume that you don't know what you're doing because you feel like there's information missing and then you just don't go down the path. Write things out and see. Because what I'm thinking is we're going to see that the mass is going to cancel. So let's see, I'll have mass 1. Well, mass 1 equals mass 2 equals mass 3 equals mass 4. So I'm not going to write that down. So mass times radius 1, radius 1 squared. And let's see, there's 4 of them, so I could write it out as mass times 1 squared plus mass times 2 squared. Plus mass times 1 squared plus mass times 1 squared. But there's really no point. We can just do this. Times omega naught is going to equal, let's see, 4 times mass times R2 squared. Omega final. Pretty cool. A couple things happen here when I look at this. I'm like, I feel like we can simplify this down, and by golly, we can. We can do this. Masses go away. And what do we have? R1 squared times omega naught divided by omega final. Whoops. Not omega final, that's what we want. Divided by R2 squared equals omega final. So there's some benefits to figuring these things out and seeing what simplifies, because it saves you a lot of button pushing. So let's see. I don't need to put in my calculator R, or 1 squared, that's just 1. And let's see, we know 4 pi. So I have 4 pi, 4 times pi, divided by 0.5 squared. And I get 50, whoops, helps if you write with the right end, 50.3 radians per second. And I apologize, I'm trying to multitask right now. It's not going very smoothly. All right, so let's compare our final omega to our initial omega. So I told you it was 4 pi, or about 12.6 radians per second, compared to 50.3 radians per second. So decreasing that radius, pulling those masses closer to the axis of rotation, sorry about that, does indeed speed this thing up a considerable amount. So let's see. This is very similar to the quiz question I gave you, where there was like a little cup thing on the disc. like this, and then instead of having the child on the merry-go-round run at the merry-go-round tangentially and jump on and make it spin, this one, in the quiz question and here, I have the child coming straight at, or whatever mass is being added to it, going straight at the thing. So if this thing isn't rotating, if the merry-go-round is stationary and I run straight at it, it's not going to start rotating. I can only get that rotation if I have some sort of tangential component, something that is perpendicular to that axis of rotation, to get it to go. Straight on won't do it. So this is exactly the same as that. I would suggest to you to give this one a go. It is identical to the quiz question, so I'm not going to put too much into it other than just kind of showing you the setup. And what I want to kind of relate it to is if you had my examples in first quarter, we used this little train car thing where we dropped the mass into the train car, and then the train car slowed down because the mass contributed to the linear momentum by slowing it down, but it didn't have any momentum in the direction of the motion, so it had no impact there. The same with the child jumping on the wheel or shooting the ball into the edge of the wheel that's spinning, like head on. It's going to slow it down by mass only. We're not going to have contributions of the tangential velocity going into the angular momentum. And that's it. So that is the last of our material for exam 1. I'm going to do just a couple small examples combining energy and momentum on Wednesday. But other than that, we'll move on to simple harmonic motion. We'll have a recording for that. And then you'll have your exam on Friday, and I know you all will do fantastic.